Okay, welcome to lecture 3.7. Okay, here I'm going to discuss, I think I'm going to do this in two lectures, 3.7, 3.8, but I'm going to discuss and identification problems. In the first one, I'm going to say why there's a problem with theta D and theta S. Later, I'll come back and talk about why NS and ND has a identification problem. Okay, so for now, okay, recall, here's the example. Um, where would I say there's only I had 5 observations. Okay, now, um, 5 observations. The first observation, okay, so there's 2 drunk drivers, drunk. Second one, drunk sober, so on. Okay. Um, this is how we'd write the likelihood function. Now we would substitute some of these p terms for these p terms down here. Okay. Now here's where we're going. Let me show you something. Notice that we're going to focus on the theta d's and theta s's. And what I'm going to do is I'm going to show you there's a way to multiply each theta, each theta d, each theta s by the same constant. Those constants are going to cancel out. And as a consequence, even when we multiply the theta s and theta d's by a constant, the p terms do not change once we do that. Okay. And if the p terms don't change, okay, notice that there's nothing else. There's no other uh, 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 no other sightings. I'm thinking of Bigfoot and Sasquatch. Okay. There's no other sightings of theta S and theta D except for the ones that are inside those P terms. Okay. You don't see any theta S's and theta D's in this L term, except you know that they're in the P's and in the P terms. Okay. So if you do that trick and the P terms don't change, that means L won't change. So that change, we multiply both by a constant. Okay. Okay. That's where I'm going. That was, I think a lot of you already get the point. But I'm going to bring it home and try to make it more concrete, flesh out this example. Okay. So remember, we have 4 parameters in our model: in S, in D, theta S. Okay. Um, okay. Suppose I told you that the following values for ND, NS, theta D, and theta S maximize L, the likelihood function. Okay, where, let's put a colon where they are. NS equals 247, ND equals 53. 53. By the way, I'm putting in whole number values. Levitt and Porter don't force NS and D to be whole number values. We'll get to that later, but theta, most important, theta D equals 0.026, and theta S equals 0.004. Okay. Okay. And suppose that at these values, L of NS and D, theta S, as when they equal those values, equals 0.00 137. Okay. um, okay. I want to focus on theta S and theta D. Suppose we knew the ND and NS estimates were the truth. You know, I'll put that in quotes. The truth. So I want to ignore NS and ND for the moment. Suppose that we got NS and ND. A magic genie came down and said, here's what the true values of NS and ND are. They're that. But meanwhile, we run our Excel program, our program, trying to maximize L, and we find that these two values of theta S and theta D maximize L. Okay, so theta D equals 0.026 and theta S equals 0.004. Maximize L. Are there any other? So we're given that's the truth. Let's say we know there's no errors in our computer program or our Excel program. So we know that these maximize it. What I'm asking you, are there any other values that also, are there any other values that also maximize L, i.e. that tie in terms of maximizing L. Okay. The answer is yes. Okay, here's one. Let's call that theta D hat, theta hat S. Here's one. Theta hat D equals 0.7 times 0.026. Theta hat S equals 0.7 times 0.004. Okay, that's my claim. Okay, that second possible set of values for theta D and theta S are just the old values times 0.7. And I claim that the likelihood function will not change. Okay, let me show you why. That is true. Okay, so first, what did I say? The value of the likelihood function equals 0.00137. Okay, so this equals 0.00137. Okay, and now let's put in theta D. Theta D was 0.026. So let's use red. Okay. Theta D 0.026. And theta S was 0.004. Okay, so all I've done, so I just put in the numerical values of theta D and theta S, at least for the first P, okay? I'm not going to do it, but you could see how I could put the same things in. It's just a little tedious, but the same values, cross out all theta D in this term, put in 0.026, cross out all theta S is 0.004. Okay, now. Okay, if I do that, plug in all those numerical values, then L equals 0.00137. Okay, So now, let me see. I'm going to use yellow. Can you see yellow? Yeah, okay. I think it works. Okay. All I'm going to do now is put in the new values, the theta hat values, and all those equal were the old values times 0.7. Okay. So the new values is of theta d hat. Oh man, I'm not sure if yellow is going to show up. Let's try it. Times 0.7. 0.026 times 0.7, 0.004 times 0.7. That's a plus sign there, plus 0.026 times 0.7 plus 0.04 times 0.7. Okay, now, if you stare at this, you'll notice that every term in the numerator has a 0.7 multiplied. It is multiplied by 0.7. Every term in the denominator, it is also multiplied by 0.7. So what can happen is if we divide numerator and denominator by 0.7, all the 0.7s cancel out. So we get that cancels out that cancels out that cancels out that. So when we multiply theta d and theta s by 0.7, p sub dd does not change at all. Okay. Now I didn't do that. To do this right, I should have done the same thing with all the p terms. Everywhere there's a theta s, I should have put in 0.04. I've done theta d here, 0.026, so on. Do the same thing, multiply all these terms by 0.7. PDS would not change, nor would PSS change. Okay, because of that, because we've put in this new values of the theta hat. That means all of these p terms are not going to change, and therefore L is still going to equal 0.0037. So what that means is these estimates do just as well as these estimates. Both of them maximize the likelihood function. There's no unique set of thetas that maximize the likelihood function. Okay, so that means we have an identification problem. Okay. And so we say we cannot identify theta s and theta d. Turns out we can identify the ratio. Okay, I said that as long as you can multiply both by a constant, and that doesn't change things. But if you multiply both by the same constant, the ratio does not change. So we can identify the ratio of theta d to theta s. Okay, and so what happens is, let's see if I can do this. Okay. Let's write on this board. Okay. To steer around the identification problem with theta d and theta s, Levitt, and Porter define theta, and that just equals theta d divided by theta s. Okay. Now, let me show you. Once you do that, so they're going to argue that you can identify theta. Okay. does that mean? Okay, let me show you. Okay, I've already put a bunch of markings for the PDD. Um, go back. Theta D divided by theta S. By the way, let's think about the substance of this for a second. Theta D is the probability of having a crash when you're drunk. Theta S, probability of having a crash when you're sober. Okay, we should think theta D should be higher than theta S. And it turns out they get that the estimate of theta is about 8. So if you're drunk, you're about 8 times more likely to have a fatal crash than when you're sober. Okay, so remember that theta D divided by theta S is about 8. Okay, here's what they do next. Okay, so we're going to change this term so that we can rewrite it so there's no theta S's and theta D's. Instead, there's just thetas. Okay, now how do we do that? What they're going to do is they're going to, I want to use red. They're going to divide this theta D. They're going to divide numerator or multiply numerator and denominator by 1 over theta S. Okay, once you do that, you get a 1 here. You get a theta D divided by theta S. Sorry, I can't write very well. Theta D divided by theta S, that just equaled theta, okay, by their definition. So here you get a theta D divided by theta S. Okay, that is going to equal theta. Here you get a theta S divided by theta S. You get a 1. Here you get theta D divided by theta S. You get a theta. Here theta S divided by theta S. You get a 1. Okay. You know what? I'm not going to do it. I encourage you, maybe hit the pause button, write down this equation. You do the same thing. Divide all the terms in the numerator by theta S, all the terms in the denominator by theta S. You want to do the same thing for this PDD term, okay? So I'm going to come back and I'm going to write the likelihood function on my own in the next lecture, okay? So that was lecture 3.6, okay? No, that was 3.7. I'll see you in lecture 3.8.